In this video, we're going to be talking about contour integration with polar coordinates. So let's say we're interested in finding the following integral, dz over z, for the curve defined by the unit circle on the complex plane. So unit circle has radius of 1. So the curve C is defined by x squared plus y squared equals to 1. The first thing we want to do is we want to find z in terms of a single parameter. So we know that z is equal to x plus I y. And the parameterization we should use, because we're using a circular arc here, is going to be the following. So we have x equals to radius times cosine of t. So t is going to be our parameter. And y equals to sine of t. And t is going to go from, because it's just an angle, it's going to go from 0 to 2 pi. And then we're going to have this means that we can write z as cosine of t plus I sine of t. And if you notice something peculiar about this is actually the same as the Euler identity, which tells us that we can write this sum as e to the power of it. And this is really nice thing, because it means that we can differentiate and integrate this function, which is a lot easier to integrate than this one. And that's going to simplify things quite a lot for us. So now we get the element dz, which is going to be equal to the derivative of this with respect to t, which is going to be I times e to the it dt. And all we do is we're going to plug these values back into the integral. So we're going to get dz over z is going to be equal to 0 to 2 pi of I e to the it over e to the it, and this is dt. And then these two terms cancel out, so you're going to be left with it from 0 to 2 pi, and that's going to give you 2 pi I. So we just found the result of that integral by using this conversion and using the Euler identity. So this is a really nice thing that you can use with complex numbers and complex integration. And using polar coordinates usually allows for this kind of simplification to be performed. So it's a really nice feature. Now let's use the same curve, but now let's evaluate a different kind of integral. So let's say we have complex conjugate of z, which is just going to be, so we're using the same curve, so we use the same parametric definition. So complex conjugate of z is just going to be e to minus it times I e to the it dt. And hopefully it is obvious that these two are going to cancel out once again. So this is going to leave us with it 2 pi 0 once again. And this is the same as writing 2 pi I. So we can usually have functions of the complex conjugate of z, because technically that's just a function of z as well. And last but not least, let's say we want to evaluate the following function. So let's have a quadratic polynomial, z squared plus z plus 1 dz, and let z be along the same curve. So we're going to use the same parameterization, which means that this is going to be equal to 0 to 2 pi of e to the 2 it plus e to the it plus 1 times I e to the it dt. So we're going to get I here, sorry, it should be integral again, 0 to pi e to the 3 it plus e to the 2 it plus e to the it dt. And now once we integrate this I is going to cancel out with the I in the denominator of each of these, so we can just write the following expression, e to the 3 it over 3 plus e to the power of 2 it over 2 plus e to the power of it from 0 to 2 pi. And this is going to give us the following. We're going to have e to the I 2 pi over 3 plus e to the I, or actually that should be 6 pi, because we have 2 pi times 3. So this little thing here should be actually be 6 pi e to the power of 4 pi over 2 plus e to the power of 2 pi. And I know what you're thinking. You probably already noticed something very peculiar about this, and this is going to be minus 1 over 3 plus 1 over 2 plus 1. And what's this equal to? Well, we know that e to the I theta is going to be equal to cosine theta plus I sine theta. So if we put any multiple of pi here, so this is just integer multiples of pi in the argument, sine becomes 0 because we know that the sine curve goes like this. For any multiple integers of pi, it is going to be 0. So all these terms are going to vanish. And then for all integer terms of cosine, we're going to have a 1. But because all of these are even integers, we're going to get a plus 1. So this is just going to be, all of these are going to be the same. This is going to be 1 over 3, this is going to be 1 over 2, and this is going to be, that should be 1, right? Because that's just divided by nothing. So in the end, we're going to get 1 over 3 plus 1 over 2 plus 1 minus the same thing, which is going to give us 0. So that's going to give us 0. So the integral of this along that curve, which is the unit circle, is going to give us this result. So hopefully this video has shown you some more applications of parametric equations and parametric curves to solve complex integrals. And in the next video, we're going to continue making more definitions about complex integrals, and we're going to use more definitions from line integrals that we have may have seen before.